Welcome to a lecture on Diffraction Part 3 in the series of our study of diffraction for Bsc IV Sem students in Paper 4 by Ms. A. Shirly, Associate Professor and Head of the Department of Physics of V.V. Sanga's Veerashaiva College, Ballari. In this lecture, we are going to study Fresnel's diffraction at a straight edge and a wire both thin and thick. Let us first study the Fresnel's diffraction at straight edge. Now consider a figure which is given below. Now here AB is the obstacle. The obstacle is at a distance small a from a slit which is illuminated by a source S of monochromatic source of light of wavelength lambda. The cylindrical wavefronts from the slit come and meet the edge A of the straight edge. Here in the figure you see XY is the cylindrical wavefront which is getting obstructed by the edge A. We have a screen at a distance small b and the screen is CD. On the screen we have a point O parallel to the point A. Now according to geometrical optics, we must get below O the geometrical shadow of the obstacle, and above O we must get a highly illuminated region. This is according to geometrical optics. But the experiments actually what they have shown is that below O there is a variation of intensity and that intensity falls rapidly as we move down, that is below the region O, and becomes totally dark after a short distance. Let me come again. What we should get according to geometric optics is a perfect shadow below O and a perfect illumination above O. But what experiments have shown is that we get below O the intensity falling continuously and rapidly below O and becomes totally dark after a certain distance. And above O, we observe alternate dark and bright bands of unequal width and varying intensity parallel to the straight edge. Now these bands become closer and less distinct as we move away, and further we see a totally and uniformly illumination. Now to explain the variation of intensity inside the geometrical shadow below O, we make use of the Fresnel's theory. Remember, what is Fresnel's theory? The wavefront can be divided into a large number of zones of small areas such that each of these zones act as a source of secondary wave. That point and that theory we are going to use in order to explain the variation of intensity below O. And also later we will explain the bands, the presence of bands, and later total brightness above O. Now with reference to the point O on the screen, the point A acts as the pole of the wavefront. Remember, xy is the wavefront and A is the pole of the wavefront. The light reaches only from the wavefront AX above the pole, and the part of AY of the wavefront is blocked by the obstacle AB. If the wavefront above A is divided into several half-period strips of rectangular area, that is zone, that are zones, then the net amplitude of the entire wavefront at O is given by the equation A is equal to M1 minus M2 plus M3 minus M4, etc. That's equal to M1 by 2. Hence, the intensity at O is proportional to M1 square by 4. As we move to a point below O into the geometrical shadow, first let us take up that study. Say to a point Q1, the pole also moves from A to P1. And gradually the first, next the first two, next the first three, etc. half-period elements of the upper half of the wave are also successively cut off by the obstacle. If the first half-period element is only obstructed, then the amplitude becomes A1 is equal to minus M2 plus M3 minus M4, that's equal to minus M2 by 2. Because alternate get cancelled, we get only minus M2 by 2. Similarly, if 2 or 3 half-period elements are obstructed, the amplitude at the corresponding point inside the shadow will be A2. That is given by A2. That's equal to M3 minus M4 plus, and that equal to M3 by 2. For the next, A3 minus M4 dash dash plus dash 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 minus M4 by 2. As the intensity is proportional to the square of the amplitude, the magnitude of intensity of the points below O decreases rapidly and becomes 0 finally. Now you know this will become square and that value goes on decreasing and at the end it becomes 0. This explains why the intensity variation is rapidly falling continuously and later becoming 0, making a totally dark region below O after a distance. Now let us understand what happens above O. The formation of bands above O. To understand that, let us again consider the figure. Now we see in the region OQ, the intensity of the light is, intensity of the illuminated region is having alternate dark and bright bands. Now consider a point Q in the illuminated region on CD on the screen. With respect to the point Q, P is the pole of the wavefront. Now for any point Q in the illuminated region, the effect due to the wavefront above the pole P has the same value and it results in the general illumination. Now depending on the number of half-period elements between the pole P and the edge A of the obstacle, the intensity at Q will be either maximum or minimum. That means depending on the number of zones. If with respect to Q only one half-period strip is exposed between A and P, then the resultant amplitude at Q will be maximum, odd number. In general, if the region PA contains odd number of zones, then the net effect at Q will be maximum. On the other hand, if PA contains even number of zones, then the net effect at Q will be minimum. Now, to find the positions, now what I mean to say is, if there are odd number of zones, we will have maximum intensity, maximum amplitude. If there are even number, we have the minimum intensity. Now, to find the positions of maxima and minimum bands and their widths, now let us consider the following. Consider the effect at point Q outside the geometrical shadow. That means above O. Now do join SQ cutting the wavefront at P. Also join AQ. The number of half period elements, that means zones, contained in PA is equal to the number of half wavelengths in the path difference. That is AQ minus PQ. Taking SA is equal to small a and AO is equal to B, we have AQ is equal to, AQ is equal to square root of O square plus OQ square. Please refer the figure. That's equal to square root of B square plus Y square. That's equal to B into 1 plus Y square by B square under square root. That would be equal to B plus Y square by 2B. Now similarly work out PQ is equal to SQ minus SP is equal to square root of A plus B whole square plus Y square minus A. That would be equal to A plus B into brackets 1 plus Y square by A plus B square under square root minus A. And PQ is equal to A plus B into brackets 1 plus Y square by 2A plus B whole square minus A, that is equal to A plus B plus Y square by 2A plus B minus A, and that finally is equal to B plus Y square by 2 into A plus B. Therefore, the path difference is given by AQ minus PQ. Substituting, we get the equation. The path difference is equal to AY square by 2B into A plus B. Now, for maximum intensity at Q, the path difference is given by the equation PQ is equal to Y square by, B plus Y square by 2 into A plus B. And that should satisfy the following condition. What condition? AY square divided by 2B into A plus B should be equal to 2n plus 1 into lambda by 2. Now we need to solve this for y, and we see that y is proportional to square root of 2n plus 1. Now for the minimum brightness at Q, the path difference should be equal to 2n lambda by 2. So we get AY square divided by 2B into A plus B is equal to 2n lambda by 2. Therefore, y is proportional to square root of 2n. Please remember these two equations, where n is a whole number or an integer which is 0, 1, 2, 3. Now these equations show that the width of the band goes on decreasing. That's the first point. With the increasing the order of the number of the band. Let me come again. The width of the band goes on decreasing with the increase in the order of the number of the band. Now the diffraction pattern is represented in the graph on the right side of the figure 1, that is above O. In the geometrical shadow, intensity falls rapidly and continuously over a short distance, and later it becomes totally dark. And above O, the system has dark and bright bands till uniform illumination results. Now, instead of a monochromatic source of light, if white light is used, what we will observe is a colored bands running parallel to the edge of the shadow will be observed. So that was a theory of diffraction at an straight edge or obstacle. Now, let us see another theory where Fresnel's diffraction due to a narrow obstacle, which is nothing but, here we take a cylindrical wire. Now, in the figure, as usual, S is a source of light or source of monochromatic light of wavelength lambda. Then there is a slit. From slit, when it is illuminated with S, we get cylindrical wavefronts. We have a wavefront XY, and now we have a real obstacle, which is a cylindrical wire of certain thickness, and let that thickness be d, small d. Now, let the wire held parallel to a narrow rectangular slit, yes, such that they are parallel to one another and perpendicular to the plane of the paper. Now, when the slit is illuminated, it gives rise to cylindrical wavefronts XY falling on the wire, and due to this, a shadow of the wire is formed between M, N on a screen EF, and the region above M, E, or the region below N is illuminated. Now that's the difference. Now look at the screen. Above M it is illuminated, below N it is illuminated. But if we have the diffraction pattern in between M and N, that is the shadow region. Now on the screen, the region above M and below N have diffraction bands of decreasing intensity and decreasing thickness or form, as in the case of straight edge. Whereas in the shadow region Mn, the intensity of illumination depends on the thickness of the wire, as discussed in the following two cases. Now this you should see: above M illumination, below N illumination, means high illumination, bright, okay, but in between M and N we have diffraction bands, and how they are having decreasing intensity and decreasing thickness are formed in the case of a straight edge, as in the case of straight edge. Now this intensity of illumination in this Mn region depends on the thickness of the wire. Now first let us take a thin wire as shown in the figure. Now you see the bands are something like this. Now in the case of a thin wire, a few half-period elements, the zones of the upper half and lower half of the wavefront, are obstructed naturally. At any point R1 above M, refer the figure please. At any point R1 above M, the obstacle produces the same effect as a straight edge. Hence, the illuminated region has diffraction bands formed. When the path difference between the rays from the pole of the wavefront with respect to the point R1 and the end A of the obstacle is an odd multiple of lambda, the intensity of the band is maximum. On the other hand, if the path difference is an integer value, then the intensity of the band has a minimum value. Now, it also can be shown that in the region below N has diffraction bands of varying intensity and thickness due to the reasons mentioned above. Now in the geometrical shadow region Mn, the intensity at the center of the shadow has maximum value. What we have? First, a bright band. This is due to the reason that waves from the first, second, third, etc. exposed half-period zones reach O with the same path traveled, and hence they produce maximum intensity at the point O. But at a point Q in the shadow region, the number of half-period zones, half-period elements that are zones are obstructed in the upper and lower half of the wavefront has different number. Due to this, depending on the path difference means BQ minus AQ, the intensity at Q will have a maximum or minimum value. Now, for a bright band to be formed, the path difference should be n lambda. For a dark band to be formed, the path difference should be 2n plus 1 lambda by 2. Now, if d is the thickness of the wire, and d means small d, and capital D is the distance between the point O from P, that is pole of the wavefront, then OQ is equal to Y for the nth bright band, and Q, which is maximum at Q and can be shown as small y is equal to capital D divided by D is equal to n lambda. Also, if beta is the fringe width, it can be shown that beta is equal to capital D by small d into lambda. This is the theory of diffraction due to an cylindrical obstacle. Now, if you have a thick wire, it is written there thin wire, but actually it is a thick wire. Or when the diameter of the wire is increased, the fringe width inside the geometrical shadow decreases. And when the wire is sufficiently thick, the fringes inside the shadow vanishes. That means we see the fringes only up to certain thickness of the wire. The intensity decreases from the edge of the shadow as we move deep into the shadow region as shown in the figure. The intensity variation of diffraction bands in the illuminated region is same as in the case of thin wire as shown in the figure in the earlier slide. So here we see how diffraction happens, and this diffraction, the bending of light, has bands above in the illuminated region, and in the shadow region we have a diffraction pattern and total darkness. In the case of an straight edge, we have seen how it is. In case of thin wire, we have seen how it is, and in case of thick wire, how it is. Now, these are the two diffraction patterns obtained by a straight edge and a wire. Thank you.